Imagine debugging a high-speed SerDes link. The return loss S11, S22 looks fine. Everything seems within spec. Yet signal integrity issue persists. I diagram shows unexpected distortion and big errors creeping. You double check the channel S parameters. Nothing seems obvious wrong. But what if there's a hidden impedance discontinuity? A minor via stub, a poorly terminated trace, or a small connector mismatch? S parameters in the frequency domain gives useful insights, but they have limitations. They don't always reveal localized impedance mismatches. They average the response across frequency, making spatial defects harder to detect. This is where time domain refractometry (TDR) become essential. TDR helps us see impedance discontinuity in time and space. It gives a direct, intuitive way to visualize how signals interact with interconnects. Today, we'll uncover why TDR is indispensable for SerDes SI debugging. By the end, you will never look at return loss alone again. Let's dive in. But first, what exactly is TDR? TDR works like a radar for impedance mismatch in PCB trace, packages, and connectors. A fast edge path is launched into the interconnect. Any impedance change, such as via, connector, or trace discontinuity, reflect part of the path. The time delay of the reflection tells us the location of the issue. The magnitude of the reflection reveals the severity of the mismatch. It directly maps impedance variation along the interconnect length. This means you can pinpoint the exact source of SI problems. Unlike S parameters, TDR gives a spatial view, not just a frequency domain response. It tells where the signal is disrupted, not just how much energy is lost. Think of it as an NRI for signal integrity, scanning deeply into your design. With TDR, we see discontinuity, stubs, and impedance transition directly. This is especially powerful for debugging high-speed SerDes systems. Small impedance variation can create reflection that degrades signal quality. By using TDR, we can detect and resolve issues before they impact performance. So, why is this especially critical in SerDes design? Return loss S11, S22 measure how much signal reflect at different frequencies. It's useful, but has significant blind spot. Return loss cannot tell where in the interconnect the issue occurs. A good return loss doesn't always mean there's no local discontinuity. Even with low return loss, mismatches at specific points can destroy signal. SerDes systems operate at very high speed, where every small impedance change matters. A via stub may be invisible in return loss, but create reflection in the time domain. The interaction of reflection can cause eyesight, jitter, and eye closure. Without TDR, you may optimize return loss, but still miss critical discontinuity. Think of return loss as a ball measurement, while TDR is a rooming view. If return loss is like checking overall temperature, TDR is like finding the exact infection site. Without TDR, debugging high-speed links is like navigating without map. TDR allows precise localization of problem areas, saving time and effort. This is why serious SerDes designers rely on both S parameters and TDR together. So, how do we actually apply TDR in real debugging? Start by connecting a high-speed TDR oscilloscope to your SerDes interconnect. Launch a fast edge into the system and observe reflections. A flat trace means consistent impedance, while spike indicate mismatches. Using the time delay of a reflection to determine where the issue is. If you see a sudden impedance drop, it could be a stub or connector issues. If there's a gradual change, it might be a trace width variation. Compare the TDR trace with layout files to correlate physical structures. Check for package parasitics, connectors, and PCB stack-up mismatches. Use TDR to verify SI before and after rework to confirm fix. Apply differential TDR for SerDes length to check skew and imbalance. You can also use eye diagram alongside TDR to correlate signal degradation. Modern tools allow overlaying TDR and S parameters for deeper insights. This method saves time, preventing endless try and error debugging. It's a game changer in high-speed SerDes link validation. Now, let's see real-world examples of how TDR solves issues. Let's start with the classic culprit, via stubs. Imagine you design a SerDes link with a well-matched impedance traces, verified in simulation. The return loss looks acceptable, yet signal integrity issues appears in the lab measurement. The eye diagram is crossing, and unexpected jitter is present. What's going on? The issue is a via stub, a leftover portion of the via that's not carrying the signal. Even though return loss didn't highlight a major problem, a TDR measurement reveals a sharp impedance dip at a specific location. This stub is acting like a resonator, reflecting energy back at specific frequencies and degrading high-speed signals. By modifying the PCB design, either using backdrawing or optimizing via length, we can eliminate the stub. Post-rework TDR shows a smooth impedance profile, and the eye diagram opens up significantly. This is a perfect example of how TDR finds what return loss alone misses. Next, let's look at how connector impedance mismatches impact SerDes performance. Connectors are often overlooked in SerDes SI design, but they can silently degrade performance. Consider a system where return loss seems reasonable, yet bit error are unexpected high. A closer look using TDR reveals the problems. A connector impedance mismatch. The connector's impedance differs slightly from the transmission line, causing the reflection right at the interface. This reflection interacts with the main signal, leading to distortion, jitter, and eye closure. By switching to a connector with a better impedance match, or carefully tune the launch geometry, we can reduce the discontinuity. The TDR trace, once showing a clear reflection spike at the connector, now appears much smoother. The result? A much cleaner SerDes eye diagram and improved bit array. Now, let's explore how even small trace width variation can impact high-speed signals. Not all impedance discontinuity come from vias or connectors. Sometimes the PCB itself is the problem. In this case, a SerDes channel shows performance inconsistency across different boards from the same batch. TDR measurement reveals the culprit. Trace width variation caused by PCB manufacturing tolerance. In some areas, the traces are slightly narrower, increasing impedance. In others, they are wider, decreasing the impedance. This creates a series of small impedance mismatches, leading to increased mode conversion and return loss degradation. By improving PCB manufacturing tolerance or using impedance control verification, we can minimize these issues. Post-rework TDR scans confirm a much faster response impedance profile, ensuring consistent signal performance across different boards. Next, let's see a case where a hidden stub resonance caused by major problem. This case is tricky. Standard S parameter shows good return loss, but the system still exhibits unexpected noise. TDR analysis was needed to dig deeper. A careful TDR scan exposed the issue, a hidden stub resonance in a multi-layer PCB design. A bird via segment, although electrical small, was creating reflection that resonates at specific frequencies. Because return loss measurement average response over frequency, this issue was nearly invisible in S11, S22 plots. However, in TDR, the stubs effect was clear. A periodic impedance fluctuation appears in the time domain trace. A redesign with a better via placement and layer transition eliminates the issue. The result? A more stable signal, reduced noise, and improved jitter margin. Finally, let's look at how TDR helps diagnose differential SerDes length skew. In differential SerDes systems, length-to-length skew is a major challenge. Even a small timing mismatch between the positive and negative signals can degrade signal quality and increase the data-dependent jitter. In this case, a SerDes system with tight timing margin shows unexplained jitter. The TDR was used to compare the differential impedance profile of each lane. The result? A slight delay mismatch between the two traces caused by a small length difference in PCB routing. This tiny skew, which didn't significantly affect return loss, was enough to introduce phase distortion. By careful tuning trace length or using equalization techniques, the skew was minimized. TDR confirmed the improvement and the SerDes eye diagram become much more cleaner. As those case study shows, TDR is a game changer for SerDes debugging. Whether it's a via stub connector, trace variation, hidden resonances, or differential skews, TDR provides clear, actionable insights that the return loss alone cannot reveal. Now, let's wrap up. Why you should always consider TDR in your SI verification flow. Here are summarized images showing you why the TDR is not just an advanced tool. It's essential for SerDes debugging. Return loss alone is not enough to detect special impedance discontinuity. TDR provides direct spatial localization of SI problems. It helps uncover via stubs, connector issues, trace mismatches, and differential skews. High-speed SerDes link demand both S parameters and TDR analysis. Without TDR, debugging is guesswork. Don't leave performance to chance. Modern TDR tools integrate well with I diagrams and S parameters. Using TDR saves time, reduce design iterations, and improve system reliability. Think of it as a must-have tool in your SI debugging toolbox. The next time your service system has unexplained SI issues, ask yourself, have I checked with TDR? If not, you might be missing the real problem. Start applying TDR today and elevate your signal integrity analysis skills. Your next step, try TDR on a real system and compare results with S parameters. Thanks for watching, and let's take your SI debugging to the next level. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.